Alright, let's open up to page 213. We're going to try some more of these related rates today. These word problems that are dealing with one rate affecting another. We're going to, again, take it a little slow today with the table format. Okay, they kind of give us the nice steps and directions to follow. I think we still have a few more with that, but eventually I'm going to take the table away and we're going to try to do them without that information or those helpful steps. Okay, so let's take a look. We'll just start off on page 213. As you're reading this or as we're going over it, try to visualize it. Okay, get a picture in your head, or maybe you want to draw one down to help you out. So a stone is dropped into a calm body of water, causing ripples to form in concentric circles. We can visualize that, right? We're familiar with that kind of scenario. The radius of the outer ripple is increasing at a rate of 1 foot per second. Thank you. All right, so let's go ahead and perhaps label this. I see the word rate, which is signifying what? A slope, aka derivative. So we're going to have d something over dt. All these are over dt's. Related rates are always looking at how something is changing with respect to time. Like as this scenario goes on over time, how are different variables changing? What might the d something be up top? Can we label what is changing in this case? dr, right? The radius of the outer ripple is increasing, so that means our rate should be positive. So dr over dt we can just label as 1. When the radius is 4 feet, okay, that's kind of our snapshot moment. Like as this rippling effect continues, if you were to take a picture of it, okay, at this one point in time, I label this as pit for point in time. Okay, this is the one moment that we're focusing on. So when the radius is 4 feet, at what rate is the total area of the distributed or disturbed water, okay, this concentric circle, changing? So how might we write or label the rate at which the total area is changing? Can we use a symbol? Yeah. dA over dt. And this is what we're trying to figure out, so we'll label it as a question mark. Okay, so that's just reading it slowly, labeling the different pieces of information. We'll probably label them later on through this chart process because it asks us to identify different pieces. So let's just take a look at part 1. Identify all the variables in the word problem. What are some different pieces of this concentric circle that we're talking about? Good, Braden?
Radius and area.
A radius and an area. Alright, so we need to figure out, are either of these variables, do they remain constant throughout this scenario? So if you were to drop a pebble and imagine the circles in the water getting larger and larger, as the circles get larger, does the radius change? Yes. Okay, so that's not going to remain constant. As the circles get larger, is the area changing? Yes. Okay, so that's not constant. So unfortunately, none of those variables that we identified are constant. It would be nice if they were, okay, because we could probably replace them with a value, but we don't. That's not the case for this question. Alright, so identify the rates that are given. We already did that at the top. We'll just label them down again. We said the rate at which the radius is changing is 1. And we're trying to figure out the rate at which the area is changing. Okay, so somehow we need to write an equation that relates area and radius, and we're specifically talking about circles. So it's either going to be something on the front of this lesson page that we went over yesterday, like the different formulas that we were practicing finding the derivatives of, or if it's not on the front page, it's probably something that you have to know. Yeah, Braden?
A equals pi r squared.
Let's do the area of a circle. Yep, area equals pi r squared. So that's a wonderful equation to use because it relates the two variables together. Let's double check this. Okay, so there are certain things that we're eventually going to have to be aware of. These first few related rate problems that we're doing are kind of simple ones, but we are going to get into more involved ones. At this stage, okay, after you have that equation that relates the variables together, you can substitute any value that represents a variable that is constant. But unfortunately, we did not list either of those variables as constant. So we can't really substitute anything in for A or R just yet. Some of you might feel the urge to substitute in 4 for the radius. Okay, but this 4 is a point in time. Okay, like one moment during this entire scenario. So you can't really use this point in time until you take a derivative. Okay, you can't plug in that 4. It's not a constant of 4. This is just a point in time of 4. Do we understand the difference between the two? Okay, so we can't substitute anything in just yet because we didn't label anything as constant. The other thing we need to check is that you can only have one more variable that you have rates. So if you take a look at your equation, you have 2 variables, which means we should only have one rate. And notice how that's the case. Okay, we only know one rate. We're trying to figure out another one, but we only know one. So you can only have one more variable in your equation than a rate that you already know. Okay, so we don't have to worry about any of those 2 other things to take into account. Okay, some other examples we're going to get to probably today, we'll see how those ones work, but not applying to this one. So far so good. Let's go ahead and implicitly differentiate. Okay, so anytime we take the derivative of something, we need the d something over dt. How do you want to represent the derivative of A? With respect to time. Like as time goes on, how do you want to represent the derivative of A? dA over dt. Alright, let's check out the right side. How do you want to take the derivative of pi r squared? Pi is a coefficient, r is the variable. We listed that up here. It was the radius. Right, let's use the power rule. We'll bring down the power of 2 in front of the pi. We'll multiply them together. Our new power on the r would be 1. And we took the derivative of r with respect to time as time goes on. So we need a dr over dt. Alright? So now that we took the derivative, let's go ahead and substitute in the values that we know. Okay, we're trying to figure out a dA over dt, so we got to leave that one blank. But if this is the one we're trying to figure out, that means we should be able to plug in some value for all the other variables or symbols that are left. So do we know a particular radius for this moment in time that we're looking for? That would be the 4, right? Do we know the rate at which the radius is changing at this particular moment in time? We labeled that as 1, right? So we should be able to calculate from there. Pretty simple. Looks like we'll have 8 pi. All right, now the last thing are the units, because this is a word problem. We have units or some type of background behind these numbers. These numbers represent something. So what do you think the units might be? This is a derivative, so we're going to have a fractional unit, something over something. You're going to give it a shot, yeah?
8%.
You're close. What do you think, Justin? Y squared. It's an area. Okay. Notice how what you're calculating is the derivative of area. So you need an area unit up top. Area is always squared. Volume is always what? Cubed. Okay, so area is always squared, so we need a feet squared. And our time unit from the scenario, if you look at the units at the top of the page in the little paragraph, we're dealing with seconds. Okay, so the derivative symbol is kind of cluing you in as to what your units should look like. You should have an area unit over a time unit. How is that related rate? That one was kind of simple. Let's try another one. All right, water is leaking out of a cylindrical tank. Maybe we'll draw a picture. Here's a cylinder. It's leaking out at a rate of 3 cubic feet per second. Can we label that value? What rate does it represent, and what number value should it be? D something over dt. Can you tell based off the units? dV, right? Cubic feet, feet cubed. Okay, that's a volume unit. And if we are leaking water, we're losing water, right? So this should actually be a -3. That might be a little tricky because it doesn't actually say -3 in the problem. But if you're losing water, your derivative or rate should be negative. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? All right, now depth of the water changing, the rate at which the depth is changing. How do you want to represent that derivative? What variable do you want to use for depth? You want to use h? Okay, so you could use d for depth. You'd have dd over dt, but another word for depth could be height. Okay, so we have the height of the cylinder. We'll let that represent the depth. We also are mentioning kind of a radius here of 4, so that might be worth noting too. All right, so based on this scenario, what are the variables that we have listed? What are some units of measure that we identified? We have volume. We listed some type of radius. And we also listed or identified some type of height or depth. All right, so imagine this scenario. Okay, you have water inside of this tank and you're losing water at some rate. Okay, as you're losing water, is the volume changing? Yeah, you're losing water, right? The amount of water that you have is changing. So that's not constant. As you're losing water, is the height of the water changing? Yeah, that's not constant. As you're losing water, is the radius of the water changing? What do you think? No, right? It doesn't matter if your water is kind of up here or maybe down here, right? Don't they always have the same radius? So in this case, we do have a variable that remains constant. We can label that as the radius. We haven't seen that yet, but this is an example of one. Okay, as the water is leaking, as this scenario continues over time, volume and height change of the water, but the radius does not. All right, identify the rates that are given. We labeled dV over dt as -3. and dH over dt is what we're trying to find. Alright, so let's kind of relate all of these variables together. Write an equation that can bring all the variables together, specifically related to whatever shape you're working with. So can we think of an equation for a cylinder that relates volume, radius, and height? Maybe it's on the front page of your notes. We might have to think about it if it's not there. What do you think, Braden?
E equals pi r squared times h.
Times h. Good. Is that on the front page?
Yes.
I think so. Okay. Alright, so here's the equation that relates everything together, but we can substitute any value that represents a constant variable. Okay, so I'm going to underline this sentence here because it applies to this particular problem. We said the radius was never ever going to change. No matter at what point in time or snapshot moment you take, the radius is always the same. What is the radius? 4. Okay, so at this moment, we're automatically going to plug in 4 because that's never ever going to change. So it looks like if we simplify it, we'll have 16 pi h. Notice how that's kind of helping us because the initial equation had 3 variables in it, right? Volume, radius, height. And since one of them was constant, we can substitute in that value. It's never going to change. Now we're only down to 2 variables. Okay, 1 less variable to work with or worry about. So if something's constant, that's going to help you out. It's going to take away a variable, which is nice. Alright, so far so good. Let's go ahead and check to see that the variables that we have are kind of making sense here. We have 2 variables, okay, v and h, which means we should know one of them and not the other. Notice how we know dv over dt, but we don't know dh over dt. So that's checking out. The variables we have left, we have the derivatives listed, but we only know one, which means we should be able to figure out the other. Let's go ahead and take the derivative so we can figure out the other rate. So how do you want to represent the derivative of volume as time goes on? dv over dt. Let's take the derivative of the right-hand side. 16 and pi are coefficients. H is your variable. You can think about it as h to the first if that helps you out. The derivative of 16 pi h with respect to time.
16 pi dh over dt.
Good. 16 pi dh over dt. So let's fill in what we know. We know dv over dt is -3. And nice thing for us, we're trying to figure out dh over dt. Maybe that I should have wrote that down here in this block. Okay. So let's go ahead and divide over the 16 pi. So as an exact answer, you could leave it as -3 over 16 pi. If you had a calculator, you could get the decimal value. I think it'd be -0.06. If you want to double check me on that. Something like that, if you round it. Okay, so either one is fine depending if you have a calculator or not. What about the units though? Take a look at your derivative to help you out. We need a height unit divided by a time unit. Maybe read the paragraph at the top to help you think about what units we're working with. What do you think, Joseph? Feet per second. We're starting to get the hang of these a little bit. Okay, it helps to label everything. Okay, double check as you go. Alright, let's try the next one. cone has a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone so that the height of the water level is changing at that rate. At the instant when the radius of the exposed surface area, wow, is 2 inches, at what rate is the volume changing? Yes, go ahead. All right, for visual sake, I'm going to draw a picture. Let's go ahead and draw a cone. And let's see, diameter of 10 inches, height 15. Water is being poured into the cone. All right. What can we label this 1.2 inches per second as? Notice how it's a fractional unit, inches per second. Fractional unit signifies a rate, aka the derivative, but which derivative do we want to label it as? dH over dt. All right. Do you think that value 1.2 should be positive or negative? Positive. As you're pouring water into the cone, the height of the water is increasing. Okay, so this should remain a positive 1.2. At the instant when the radius of the exposed surface area is 2 inches. So this is your point in time. Notice how it said at this instant, okay, at this moment. So your radius is 2. If you think about this, okay, visualize it in your head. As you're pouring water into a cone and you were to look down into that cone, what shape would you find? What would the water look like? It would look like a circle, okay? So the exposed surface area is actually representing a circular shape. I know we're talking about a cone, okay, but if you were to look down in it, the exposed water you see would be a circle. So the radius of that circle is 2. Even though the radius of the cone is 10, maybe this radius right here is 2. Okay, that's how much water we have enough water in there to have a radius of 2. What we're trying to figure out, the rate of volume. So that would be dV over dt. All right, let's go ahead and label some variables. Based off of what we have kind of jotted down so far, we listed a dH over dt. That variable is specifically a height. We also know a point in time dealing with a radius. And we're trying to figure out the rate at which volume is changing. So volume can be another variable. Are any of these, yes?
Is diameter not a variable?
Diameter we could say is related to a radius. Okay. All right, as you're pouring water into this cone, is the height of the water changing? Yes. As you're pouring water into this cone, is the radius of the water changing? Yes. As you're pouring water into this cone, is the volume of the water changing? Yes. None of those are constant. So unfortunately, we can't plug any number in to get rid of a variable. But at least we know that. Identify the rates. We already did that. We'll just list them down again. dH over dt we said was a positive 1.2. And dV over dt we're trying to figure out. Alright, so let's go ahead and think about, we need some type of an equation specifically for a cone that brings together volume, height, and radius, the 3 variables we listed. It's either on the front of the page, which means I'd give it to you, or it's something you have to know. Can we find it? Volume of a cone?
V equals 1/3 pi r squared times h.
1/3 pi r squared times h. Okay, so there's our equation. Let's double check some things. At this moment, okay, once you find your equation, you could substitute in any value that's constant, but unfortunately we said there weren't any, so we can't get rid of a variable. Let's check the other thing. It's important to keep in mind that you can only have one more variable than you have a rate. You have 3 variables listed in your equation. How many rates do you know? 1. We have an issue, right? Okay. Notice how we know a dH over dt, so we want to keep an h in there. We're trying to figure out a dV over dt, so we want to keep the v in there, but it seems like the r is the issue, okay, because we don't have a rate for r listed. So what we're going to have to do is be a little tricky here. You may have to make a substitution that relates one variable in terms of another. Okay? So let's think about this. They specifically mention, probably for good reason, in the very first sentence that we have a 10-inch diameter. By the way, if the diameter is 10 inches, what's the radius? 5. Okay, so we know we have a radius of 5 at the, this should be 5, not 10. Alright, so we have a radius of 5 at the top and a height of 15. There's some connection there between the two. And what's nice about that connection is that ratio or relationship between them is going to remain constant throughout the entire cone. So for instance, if you were to compare the radius to the height, we could probably substitute something in here for r to get rid of that variable, because the r is the issue. We don't have a dr over dt listed. So we want to replace the r with a v or an h, because those are the rates we have. So using this 5 and 15 they gave us, let's go ahead and create some type of proportion or relationship. We could say that the radius compared to the height is 5 over 15. Notice how that relates one variable in terms of another. Okay, we're relating r and h together. If we want to replace the r, because that's the issue variable, the one that's presenting a problem, let's go ahead and change this into r equals. That way we can substitute it in. So we could multiply the h over, and maybe we want to simplify 5 over 15, which would be 1/3. So throughout this entire cone, no matter what height or level of water you have, the radius of the water is always going to be 1/3 the height. Okay, no matter what point you are in this water pouring process. Okay, we have a way to connect the two. So let's go ahead and replace that in for r. Can we simplify that a little bit? Because it was r squared. If we're plugging something in for r, we're going to have to square that value. Let's see, 1/3 squared would be 1/9. And maybe we can multiply that with the 1/3 that was already out front. 1/3 times 1/9 would be 1/27. We still have the pi. And then we're going to have an h squared times an h, which would leave us with an h cubed in the end. Alright, so check out your equation. How many variables do you have now? 2. How many rates or derivatives do you know? 1. You see how we have one more variable than rate? We're good to go. And specifically, those variables we know are v and h, and notice how those are the derivatives we have listed, dv and dh. Everything's kind of matching up. We got rid of that r variable that was our issue. Okay, so since this is now checking out, the variables match the rates that we have listed, let's go ahead and take the derivative. Okay, so I think we're getting pretty good with this so far. We would have dv over dt on the left-hand side. What about the right? 1/27 and pi are coefficients. H is your variable. If we were to bring down the 3, we would have a 3 over 27, which can simplify to 1/9. We still have the pi. We now have an h squared because we got to take 1 away from the power. And we took the derivative of an h variable, so we need dh over dt. Are we doing okay so far? Okay, this one's a little tricky because we had one more variable than rate, so we had to somehow replace that variable in terms of another variable that had a rate that we identified. Okay, so everything has to be kind of organized and matching up. Let's go ahead and plug in what we know. Do we know a dv over dt? Unfortunately not. That's what we're trying to find. But in order to figure out dv over dt, we should be able to fill in the other variables or derivative rates that we have listed. So at this moment in time, at this snapshot moment, do we know what the height is of the water? Not quite, right? We know the radius at this point in time, right? The radius is 2, but we don't know the height just yet. Okay, so maybe we'll leave that blank for now. Do we know the rate at which the height is changing? Wasn't that 1.1? Or sorry, 1.2? All right, so we're so close. Somehow we got to fill in something for h. So we should have something listed so far that could help us figure out the height. We know the radius at this point in time, so how can we figure out the height at this point in time? Yeah?
Plug 2 in for the r equation.
Which one?
R equals 1/3h.
Let's take a look at that. That equation we wrote that related height and radius, okay, connected the two together. If we know the radius at this point is 2, we should be able to figure out the height because we have a connection between the two variables. So divide over 1/3, multiply by 3, whatever you want to do. Looks like the height at this point in time is 6. So we'll go ahead and substitute that in. So they were kind of doubly tricky with this one. They gave you an equation that involved replacing one of the variables, but then they also gave you a point in time that wasn't necessarily needed for the equation. You had to use that point in time to figure out another point in time, okay, for a different variable. Doubly tricky. But we filled everything in, which means we should be able to simplify. So this one I would say is a calculator one with the decimals and the 1/9. If you have one available, can you help me out once you type everything in? Did you get something?
I got something.
Go ahead.
15.07.
07 what? 079. That's fine. Okay. Looks good. What about our units? Look at the rate to help you out. We need a volume unit divided by a time unit. Go back to the paragraph at the top to take a look at what you're specifically talking about. Inches cubed. Yep, we need a cubic unit for volume. And looks like our time unit was seconds. All right, we'll see if a few more of those types as we go through some more examples. That one was doubly tricky. We hanging in there though? Anyone hot? I'm getting hot. Yeah. I'm gonna shut the heat off. And hopefully I don't smack you in the process. All right, so we're going to step it up a bit. We're going to take the chart away, okay, but we're going to try the same steps, okay? So we got to identify variables, rates, think of an equation, take a derivative, make sure everything checks out. We'll draw a picture too, okay? Visualize it, get a picture, try to see it. A ladder 25 feet long is leaning against the wall of a house. All right, so I know we're not exactly Picasso's in here, but just draw something to help you visualize it. There's my ladder against the house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So if you were to imagine the bottom of this ladder being pulled away, it's kind of being moved in that direction. If the base of the ladder is being pulled away, what's happening to the top of the ladder? It's going down, right? Can we visualize that? It looks like our geometric shape is a triangle, so maybe we'll label the base and the height and the hypotenuse as some different variables. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So based on the variables that I used, you could use different ones like A, B, or C, okay, whatever you want to label. How might we identify this rate? Can we use a derivative notation to help us with that? The base of the ladder. dx. Okay, so dx over dt is 2. You got to figure out, is that 2 positive or negative? Now, x is representing kind of the base of that the base of the triangle, right? As the base of the ladder is being pulled away, is the base of the triangle getting smaller or larger? Larger. So this should be positive, right? You're growing. So even though the language is kind of tricky, okay, you see pulled away and you might think negative, but actually when it's being pulled away, this distance is increasing. So I would highly suggest drawing a picture because sometimes the wording could be a little misleading. All right, so this information, notice how it was given at the top portion. So this information applies to part A, part B, and part C at the bottom. Okay, if it's given at the top, you can use it all the way through. But if something is given in part A, that doesn't necessarily mean it applies to part B. You have to be a little careful with that. It could apply, but it might not. So let's check out part A. How fast is the top of the ladder moving down the wall? Makes sense, because we said it should move down. When the base of the ladder is 7 feet from the wall. So how might you want to represent how fast, and how might you want to label when the base of the ladder is 7 feet? Can we use some symbols, notation? How about the first one? How fast is the top of the ladder moving down? Yeah.
dy over dt.
dy over dt. How fast, meaning a rate of change. So this is what we're trying to figure out. What about the 7 feet from the wall? Is that an x value, a y value, a z value? That's an x value, and specifically that's a point in time. Okay, when this happens, that word when is kind of a clue word for point in time. Alright, so it looks like we have everything labeled. Our variables are x, y, and z. Somehow we need to think of an equation, or let's think about this. Are any of these variables constant? As the ladder is sliding away, does x remain constant, y remain constant, z remain constant? Are they all changing? What do you think?
Z is constant.
Z is constant. Okay, z is the ladder itself. So as the ladder is sliding away, it's not like the length of the ladder is changing. So maybe we'll label this one as constant, which would be good to know. So let's try to think of an equation. We're dealing with a circle, specifically, not circle, oh my gosh. We're dealing with a triangle, specifically a right triangle, because it's against the side of a house, perpendicular sides. And we need an equation that relates x, y, and z. Anything pop out at you? Pythagorean theorem. Alright, x squared plus y squared equals z squared. Now, we did label z as constant. So that means, before we even take the derivative, before we get too far ahead of ourselves, we should be able to plug something in for z, because it's never ever going to change. What is the value of z? Do we know that? 25. The length of the ladder they said was 25. Alright, so that's good to know. The other thing we got to check is to make sure that the variables we have listed in our equation match the derivatives or rates that we have identified. Notice how we have an x and a y in the equation, and we have labeled a dx that we know and a dy we're trying to find. Do you notice how we don't have an extra variable in there that doesn't have a derivative we listed? We don't have that issue of r, or the radius, like the cone example. Okay, everything's checking out. So let's go ahead and take our derivative. With respect to time, derivative of x squared, 2x dx over dt. Derivative of y squared with respect to time, 2y dy over dt. Derivative of 25 squared, 0. That's a number, right? Alright, so we're trying to figure out dy over dt, which means we should be able to plug in some numbered value for every other variable or symbol. Do we know an x value for this point in time, this snapshot moment? Yep, that was 7. Do we know the rate at which the x is changing at this moment in time? We said 2. Do we know a y variable for this point in time? It wasn't explicitly given to us, right? But that doesn't mean we can't figure it out. So maybe we'll leave that blank for now. We're trying to figure out dy over dt, and we know this should equal 0. So the only thing we got to be kind of not curious about, but tricky about, is figuring out this y value. At this moment in time, can we figure that out? At this snapshot moment, we know the ladder is 25 and the base was 7, right? Can we figure out why? Alright, we're going to plug it back into this Pythagorean theorem to help us figure that out, okay? But you guys got to go to lunch, so we'll do that tomorrow. Okay? How are we doing without the chart or the steps? We doing okay? All right, we're going to keep doing more tomorrow. Practice, practice.
Tomorrow your last day?
Tomorrow's my last day.